how do we think we did on that quiz? Felt pretty good or terrified? Okay, despite not studying over the weekend? Okay, all right, well good. I mean, that just means we knew it so well we didn't need to study. Maybe that's what it was, right? Anyway, hopefully if you're watching, you did well on your quiz also. Let's take a look at the homework that you did over the weekend on page 264. You had just 3 questions to answer. Questions 1, 3, and 4. So books open to page 264. Question number 1 asks this: through what media can sound travel, and through what can it not travel? And what did you have? Kendall?
The media that sound can travel from is elastic medium. It cannot travel through a vacuum.
Good. Any media that is elastic, sound can travel through. It cannot travel through a vacuum. And really, truly, all media, to some extent, is somewhat elastic. I mean, some of them are barely elastic. But, yeah, basically, it just can't travel through a vacuum. Number 3, why does sound travel slower in a piece of wood than in the same size piece of aluminum at the same temperature? A couple different answers we could have here. Audrey?
At the same temperature, a piece of wood has sound travel through it slower than an aluminum piece because it is harder and more dense than aluminum.
Well, you're right that it's more dense than aluminum. I would say you'd be wrong that it's harder. Aluminum is harder. Now, again, aluminum foil, not, but like actual aluminum, if it were the same size piece, wood is more dense, and wood is also less hard than aluminum, and both of those are reasons why sound would travel slower. Number 4, what's the speed of sound in air at 0 degrees Celsius, Michael?
The speed of sound in air at 0 degrees Celsius is 331.5 meters per second.
Excellent job. Good. Turn back to the beginning of the chapter, if you would, please. Page 252. We see the ancient philosophical question pictured for us there as a tree has fallen in the forest. And the question is, if a tree falls in a forest, does it make a sound? Well, depends on how you define sound. Sound, here's your definition for it. You get in your notes as we start this next chapter. Chapter 16 was an overview of waves. Chapter 17, we're going to specifically look at sound waves. And so what is sound? Here's your definition. It is a longitudinal wave that travels through elastic media. Sound is a longitudinal wave, that means a series of compressions or rarefactions that travel through elastic media. Sound, longitudinal wave that travels through elastic media. So here's the question: when the tree hits the ground, will there be a series of compressions and rarefactions that emanate forth from the site of the crash, class? Reasonably, we can say, even if no one was there to see it, that sound was generated based on what we've observed from other trees perhaps falling. Now, we don't necessarily, if no one's there, we don't necessarily get the sound of timber. We don't hear that, okay? That was my imitation of the beaver. But anyway, we don't hear timber, right? But we do hear the crash, right? The compressions and rarefactions, reasonably one can assume they emanated forth. Did it make a noise? Well, if we define noise as the perception of sound, if no one was there to hear it, one could argue it did not make a noise, but it did make a sound, right? Kind of like the ancient question, if a man speaks in a forest and there's not a woman around to hear him, is he still wrong? We don't know, right? Anyway, and Audrey's like, yes. Anyway, you're mean. Anyway, so sound is just a longitudinal wave that travels through elastic media. So here's the question then: what would affect how fast sound travels? Because right, we recognize sound travels very, very quickly. Now, does sound travel as quickly as light? No. Light travels faster. For instance, in track and field, anyone watch the Olympics? Not this past year necessarily, because it wasn't this past year, but you've seen Olympic events, sprints, that kind of thing. How do they start races in the Olympics? Fire a gun, right? The starting pistol, right? Bang. Okay? And they do this in high school track and field as well. I ran a lot of track and field in high school. And one of the races, the 100-meter race, there's 2 ends of the track. There's 2 straightaways, there's 2 curves. This guy with the starting gun stands at the far end of the track, or the guy with the starting pistol stands at the starting line, but the timers, all the guys with the little stopwatches, they stand at the other end of the track. And the gun goes bang, they start the stopwatches, the runners run down. Well, on the 200-meter, they actually start on a curve. So they start on the curve and they finish the straightaway. Well, at this point, they're on the opposite corner, if you will. I know technically there aren't corners on a track, but the opposite corner of the track. At this point, they're that much further away, and you literally can tell a difference between the cloud of smoke that comes out of the starter's gun and the sound. And so the starters are told, start your stopwatch. These are track meets that don't have the cool clock, okay? The 3 or 4 teams get together, hey, let's have a practice meet kind of thing. They're told, start the stopwatch when you see the smoke, because you'll see the smoke literally a split second before you hear the bang. So you can actually tell the difference between sound traveling and the light traveling, if you will. And but there's different things that affect how fast sound travels. I noticed in my neighborhood, I live next to some train tracks, and I noticed in the summertime, I'd hear a train coming. And I knew if right when I hear the first train whistle, they're used around the bend a little bit, if I hurry up, get in the car, drive, I can get across my train track crossing before the train gets there. So I just got used to that. Every morning it seemed over the summer, train would come. Oh, I hear the train time, I gotta really book it now. So book it, get out there, drive, get across the train tracks before the train gets there. Well, wintertime rolls around, and I got a little bit of work to do over Christmas break, and so I hear the train coming, get in the car, drive. I got stuck. Sound didn't travel as fast. Why not? Sound travels at different speeds through different things. And so first thing we want to talk about with sound is how fast sound travels. Factors affecting the speed of sound. Factors affecting the speed of sound. 3 factors affect the speed of sound. If you're looking at page 253, by the way, you will see a table there that lists how fast sound travels in different media. You see how fast sound can travel through some different gases. You see how fast sound travels through different liquids. You see how fast sound travels through different solids. And there's all these numbers are different from each other. 3 basic factors that affect the speed of sound. First factor, hardness. And in parentheses, you could put rigidity. Hardness or rigidity. Well, obviously, this is a factor that only would affect solids, right? Liquids don't have rigidity. Gases don't have rigidity. So this is a factor that only really affects solids. But for a solid object, sound will travel through that solid object based on its hardness. If you note this, it's what I call a positive factor, meaning an increase in rigidity or hardness will increase the speed of sound. They work hand in hand. So I call this a positive factor. More rigid substances, harder substances, allow sound to travel through them faster. Y'all remember maybe you've seen some cartoons or old Western movies, and you got the Native Americans, indigenous persons, they call them Indians in the movies, and they're there and they don't like the train running through their land. It scares off the buffalo, makes it hard for them to survive. They had a legitimate gripe, and so they want to know when the train was coming because they thought if they could stretch a rope across the tracks, they could derail the train. How many know what I'm talking about? You've seen that maybe in the cartoons as the Indians stretched the rope across. Well, how did they tell when the train was coming? Cartoons, they put their ear down on the tracks, right? Now, if they left it there too long, that was a bad day for the indigenous person, right? But hopefully they sensed that the train was coming a long way off. They got their buddies together and they did what they could to attack the train and make the train's life miserable, which was a sad day if you were the conductor of the train or related to him or had stuff on the train that was important to you, or you were on the train. That was also a bad day. Anyway, but the reason they put their ear to the train tracks versus their ear to the ground. Now, they would also put their ear to the ground in some cases, right? To tell, is there a herd of buffalo nearby or something like that. They could hear because the ground allows sound waves, those compressions and rarefactions to travel through it as well, right? If you get really, really strong waves, seismic waves, you got the earthquakes, right? Those are waves that actually result in displacement physically. But even so, even sound waves travel through the ground, but they travel faster through the railroad tracks, right? The railroad tracks are hard, made of steel or iron or whatever they were made of from that day. And so they were harder. They allowed sound to travel very quickly. Why? Because that which is rigid recovers its original displacement very, very rapidly. By resisting deformation, as compressions and rarefactions travel through, they travel through very quickly because there's a minimal amount of displacement of particles. Second factor that affects the speed of sound is density. Density. Density, again, is typically it affects all states of matter, but especially we think of it with solids, is a negative factor. Density is a negative factor. Those substances that are more dense have slower sound traveling through them. Why is that? Well, because as the sound has to travel through, again, these are compressions and rarefactions, very, very dense substances, there's a lot more particles to have to displace. Again, the atoms in a solid are vibrating in place anyway, right? So displacing them a little bit isn't that hard, but if there's a lot more of them tightly packed, that's going to be more of a challenge. So for instance, you look at the solids, one of those solids stands out as a very small number compared to all the others. And that would be, of course, lead. Compared to all the other substances, all the other solids, sound travels very slowly through lead. Why? It's so much more dense than the other ones mentioned there. Okay? So density is a negative factor. If you want to think of air, for instance, right? There's different gases listed there. Well, the densest of the gases listed is carbon dioxide. Notice it has the slowest speed. The least dense of all gases is hydrogen, and sound can actually travel faster through pure hydrogen than it can through some liquids even. So density, if you'll note, this is a negative factor. The denser a substance is, the slower sound will travel through it. So hardness, class, we said, is a positive factor, while density is a negative factor. By the way, pretty much all the solids, sound travels faster through solids than through anything else because hardness is such a major factor. There is no hardness to liquids and gases. There is only hardness to solids. And solids transmit sound, other than lead in some cases, other than lead, solids transmit sound faster than other substances, other states of matter. The last factor is temperature. Temperature. Now, this primarily affects gases, though it does affect other substances as well, warmer liquids, warmer metals, unless, of course, you start to melt the metal. Okay, so if you heat the metal so much it starts to turn molten metal, it gets soft. Okay, well, now you've lost hardness. Okay, so other than that, we would say that temperature is a positive factor, but it especially affects gases. Temperature is a positive factor, but especially affects gases. This is what I referenced earlier when I talked about hearing the train coming. Oh, let me get in the car, let me drive, and get across those railroad tracks before the train gets here. Well, it didn't work so well when it's cold outside because the colder air transmitted sound slower for a couple of reasons. Think about it. What happens to a gas as you heat it? It expands, right? Which makes it less dense. And we already said density is a negative factor. So for one thing, the cold air is just more dense in the first place. For another thing, not only is it more dense, but the particles themselves don't move as quickly, right? The particles are moving more slowly versus fast-moving particles. So if the particles, for instance, of a warm solid are already vibrating more, of a warm liquid are already moving around more, for a warmer gas are already freely flowing with more energy inherently, they're already got more movement already, so they can carry the sound more quickly through. So temperature is a positive factor. It increases the speed of sound, but most notably in gases. You need to write this down that at 0 degrees Celsius, in what we would call typical air, right? At 0 degrees Celsius, the speed of sound in air is 331.5 meters per second. Speed of sound in air is 331.5 meters per second. Now, here in Columbus, Georgia, sound does not travel that slowly very often, okay? Because it's not 0 degrees Celsius very often. Even this morning, it was kind of chilly. It wasn't that chilly, so sound wasn't traveling that slow. So what we need to do is we need to find a way to change the speed of sound based on temperature. So that gives us the first equation, which I'm going to say V sub air, meaning speed of sound in air. We're going to use 331.5 meters per second as a starting frame of reference. That's at 0 degrees Celsius. But remember, we said that volume and temperature are directly related. We know then that as the volume increases, that affects the speed of sound because it affects density. So it makes sense then that this speed of sound change would kind of fluctuate in accordance with temperature. And it does according to absolute temperature. Well, here's the problem. We measure things in Fahrenheit, don't we? The rest of the world measures things in Celsius. But Kelvin is absolute temperature. So what we're going to do is we're going to take the Celsius temperature, add 273, and then divide by 273 to get a relative absolute temperature. Now we're like, but we use Fahrenheit. I know, if I give you Fahrenheit, we'd have to change to Celsius first, but we're doing what the rest of the science community does here. If you add, now you say, isn't it 273.15? Yes, but by the time you add that, divide by, and then take the square root, it's really no different. So we're saving a few keystrokes of the 0.15, okay? So we're going to say, add 273 to Celsius, divide by 273, take the square root. That relationship, that multiplied by the 331.5 meters per second, shows us what the speed of sound would be in different temperatures of air. So this is the first equation we need to know. The second is actually a repeat of something from last chapter, and that is V equals lambda F. Wavelength and frequency are still related, as their product gives you speed. And this is true for sound waves as well. The wavelength of a sound wave times the frequency of the sound wave gives you the speed of that particular sound wave. So speed of sound equals wavelength times frequency. Now, more to the point, we're going to talk about this a little bit later on in the chapter, but different frequencies of sound have different pitches, right? A higher frequency and a lower frequency, right? So frequency, speed of sound, depending on the medium, is pretty stable. So what's really going to change is not so much the speed, but the wavelength will change based on frequency. And so we'll often change this equation to find the wavelength based on the frequency that is emitted. But it's still an equation that's a repeat from past chapters. All right, so then let's take a look at some example problems. It's page 254 now. Go ahead and turn over. And read the first example problem for us, if you would, Kendall.
A sound wave has a frequency of 440 hertz. This is a note A above middle C on the piano. What is the wavelength of the sound wave A in air at 0 degrees Celsius, B in seawater, and C in glass?
All right, so Audrey knows what we're talking about. Do y'all know what we're talking about? The A above middle C, or are you like, no piano, me, we're not friends. We are not well acquainted. No, okay, so you know what we're talking about. Okay, so it's not actually the center note on the piano. They just call it middle C, because that's where most of where we play would start. You play up higher than that, it sounds high. You play lower than that, it sounds low. Right around there is kind of middle ground, so it's a great place to play. Well, A is a few notes higher, I guess 6 notes higher on the piano, and it happens to have a frequency of 440 hertz. That's kind of what defines the note. And so the question is, if it were a really cold day and Audrey were playing a concert outside, they roll the grand piano out in front of the church, and Audrey's playing, and people are walking by on a cold day to hear her play, and she hits an A. Okay, they're going to hear 440 hertz. The question is, how long is the wait from one set of compressions to the next set of compressions? What is the wavelength? Well, coming here, we know that in air at 0 degrees Celsius, which is the example here, the speed of sound class is
331.5.
And we know that the wavelength of that particular note that Audrey's playing is
440.
440. Now it says hertz. Hertz is really what? Per second, right? So notice that the per seconds will cancel, and we'll get our answer in meters. If you could see the sound wave traveling through the air, what would be the wavelength of the sound wave?
0.7534.
Okay, round it off to, I think is it 2 or 3 sig figs in this? It is 3. So round off to 3 sig figs, class.
0.753
And wavelength we said is measured in?
meters.
Meters. So if you could actually see it from one compression to the next compression, it'd be about, I think that's about 75 centimeters there. That's the distance between compressions, if you will. All right, questions on the first part? Well, let's suppose that Audrey takes her piano down to the beach, and she is playing her songs down by the water as the waves are rolling in. Well, the waves aren't rolling in, it's nice still water, so we don't have to hear anything else. And Kendall's like, you know, it's freezing cold outside. It's the perfect time for a polar bear dip. So she jumps into the water, and she's there underwater as she hears Audrey strike an A. Now the A transfers through the air, it travels into the water, and she hears the A. Sound travels faster, though, through seawater. So instead of a speed of sound of 331.5 meters per second, looking back at the previous page, how fast does sound travel through seawater?
4,700.
4,700.
Oh wait, that's feet per second.
That's feet per second. Well, let's stick with meters per second. That make it a little more fair.
1,450.
1,450 meters per second. All right? So now, how long between compression pulses would there be to Kendall there in the seawater? 3.295,
95.
blah, blah, blah. About 3.30 meters then from one compression pulse to the next if she would happen to be in seawater. Let's suppose Audrey's giving her concert and she is in a soundproofed room, and except for a glass door or maybe a glass window. So if you're standing outside, you really can't hear much, but if you put your ear to the window, you can hear her play and be blessed. And the question is, how long would the wave be? What would be the distance between compression pulses in glass? Well, sound travels even faster through glass, right? So change the speed of sound again, this time for glass.
5,503.
5503 meters per second. And we divide, and what would be the wavelength in the glass? 12.56 blah 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 meters. So around about
06.
12.06?
506.
506. Okay, so we're around 12.5. 12.5 meters. Now think about this now structurally though. Imagine if you've got a window that, 12 meters, that's about 30 something feet. This is a huge, about a 40 foot actually, about 40 foot pane of glass. And you play that A. That fits the compression pulse from start to finish. You could potentially have problems there. Do you see how that can be a problem if you have a compression pulse start and then another compression in the same pane of glass? And this is why panes of glass are smaller than 40 feet long, so you don't have those same issues. Now, if you were to increase this number though, what would that do to the wavelength? As this number gets bigger, if you make a bigger denominator, it's going to shrink that. So imagine a really high frequency sound. You'd have a much shorter wavelength. Are you starting to see where I'm going with this? And so this is where design features, things like that come into play, is making sure that panes of glass are the right size for different frequencies that may be commonly emitted. But anyway, questions on just seeing how the wavelengths differ depending on the media through which sound is traveling. Make sense? All right, example 17.2. Let's suppose that we were curious about something. Remember we said temperature affects the speed of sound, right? Temperature is a positive or negative factor?
Positive.
Positive factor. Increased temperature, increased speed of sound. So for instance, King Nebuchadnezzar, fiery furnace. Shadrach, Meshach, and Abednego. Okay, sound travels, sound travels. Once it gets near the fiery furnace, it travels faster, right? Because it's really hot in there. Let's suppose it was 600 degrees Celsius in fiery furnace. How fast would sound have traveled in fiery furnace? And if it was, maybe they weren't trusting God, get us out of here. Sound travels very, now of course, as soon as it hits the cooler air, away from the fiery furnace, it slows down, and by the way, would refract toward the normal because it would be slowing down. Anyway, how fast would sound travel in air at 600 degrees Celsius? Well, in for T sub C class, we plug
600.
600. We add 273 to get the Kelvin temperature, approximately. We divide by 273 to get the relative temperature, but it's not linear progression. It's not that as the temperature increases a degree, speed of sound in air goes up. No, it's a square root relationship. So we take the square root, then multiply by 331.5. And I botched something here. Times. I thought I hit times already. Apparently not. 331.5. How fast is sound going to travel through fiery furnace?
592.
592.8 or 503 meters per second, if it were that hot. Okay, hopefully you're never in a place that's that hot. All right, questions on that? All right, turn to the back of the chapter now, page 265. And take a look at problem number 3. Go ahead and read problem number 3 for us here on page 265. Audrey?
Determine the velocity of sound in air at an altitude of 19 kilometers where the temperature is negative 52 degrees Celsius.
Now, there is just one little problem. 19 kilometers, that's, oh goodness, that's about 12 miles, about 12 miles up. So it's higher than Mount Everest, okay, but it's not necessarily, in fact, it's higher than where airplanes are flying. It's not as high as the balloon. Actually, no, that is about where that 60,000 feet, that'd be about 60,000 feet then. That'd be about where that balloon was that we shot down. Okay, so up there, if somebody were on the balloon, they'd have to have like breathing apparatus and lots of warm clothing, an astronaut suit pretty much. But they had a space suit on and they were on the balloon, manning the balloon. There was no one on the balloon. We actually don't know what was on the balloon yet. But what would be the speed of sound in air if a guy up there was like shouting to a guy in another spy balloon that we just didn't see? Hey, have you seen anything yet? Or however he says it in Chinese. And there's just a couple of little issues here. Now we know the temperature of the air, correct? Which, by the way, actually I believe air would be hotter up there than it is here. It's just more sparse. But the perceived temperature, negative 52 degrees Celsius. The 19 kilometers, that means the sound is more sparse, the air is more sparse, right? So density is affected. We're not able to account for the density in the problem. I believe the temperature accounts for the density here, the perceived temperature. But let's just say air was negative 52 degrees Celsius. We said at 600 degrees Celsius, it's 593 meters per second. What about a negative 52? Match your seats. Sound would travel a little slower up there if those things were all accounted for correctly. And how fast would sound travel up there, class? About 298 meters per second. Did we get that answer? Again, just plug the negative 52 in, add the 273. Now again, here's where Kelvin has to come in. Can you take the square of the negative, class? Imagine if we try to just roll with the Celsius temperature. We'd have a problem, wouldn't we? So by changing it to the absolute temperature, we're not taking square roots of negatives. And it is, again, that square root relationship that exists there. All right, questions on problem 3. Let's go back to problem number 1. Read number 1 for us, Michael.
The audible frequency ranges from 20 Hz to 20,000 Hz. What is the audible wavelength range in air, freshwater, aluminum, and aluminum? Assume 0 degrees Celsius and use meters.
Okay, so we've got air, which is, lots of nitrogen, a little oxygen, a little CO2 mixed in just for good health for the plants. Some fresh water and aluminum. Now, it says audible frequency. Audible means that which you can hear. We're going to talk about this a little later, but the lowest frequency the human ear can detect is 20 hertz. The highest frequency a healthy human ear can hear is 20,000 hertz. Those are the frequencies. But again, we said that as the frequency changes, so does the wavelength. High frequencies have really short wavelengths. Lower frequencies have much longer wavelengths. So the question is, what are the wavelengths of sound waves at 0 degrees Celsius in each of these media? Let's start with 20 hertz. Remember, wavelength, wave speed, frequency related by what equation, class? V equals lambda f, and therefore lambda equals V over f. So in air, 0 degrees Celsius, what is the speed of sound, class? Memorized value. 331.5 meters per second. Divide that by the frequency, 20 hertz, and what is the wavelength of the lowest sounds that our ears can detect? About 16.6 meters. It's a really long wave. In freshwater, air travels a little faster. Or sound rather travels a little faster. In freshwater, what is that speed of sound? Meters per second? I thought that was in seawater. Didn't we just use that number?
1435.
1435 in freshwater?
Yeah.
Oh. Well, anyway, we would divide that by the frequency, and we can do the same for aluminum. We don't necessarily have to finish out this problem. Just kind of wanted to show you how the wavelengths differ depending on the frequency there. All right, homework for this evening. I need you to read pages 255 to 259. Read pages 255 to 259. And we'll pick up with our discussion of sound tomorrow. Read 255 to 259 on pages 264 to 265. Answer questions 6 through 8, 10, and 11. Questions 6 through 8, 10, and 11. And do problems 2 and 4. Problems 2 and 4. Read 255 to 259 on pages 264 to 265. Answer questions 6 through 8, 10, and 11, and do problems 2 and 4. Have a wonderful rest of your day. We'll take a look at those quizzes tomorrow. You are dismissed.